Recording in progress.
Last talk for the Cairo colloquium for this semester. And today we have Owoyele, and he's an assistant professor in the Department of Mechanical Engineering here at Louisiana State University. And he will talk about machine learning techniques for simulation-driven design optimization. And before we listen to his interesting talk, I want to read a little bit out of his short bio so you know the speaker a little bit more and his background. And Owoyele has been an assistant professor of mechanical engineering at Louisiana State University since August 2021. Before joining LSU, he was a postdoctoral appointee in the Computational Multiphysics Research Station at Argonne National Laboratory. Prior to this, he was a recipient of the ORISE Postgraduate Fellowship to perform research at the National Energy Technology Laboratory, and he obtained his master's degree and PhD degree in mechanical engineering from North Carolina State University. And welcome, and we're looking forward to your talk.
Thanks, Patrick, for the introduction. So like Patrick said, I'll be talking about machine learning techniques for simulation-driven design optimization. And I'd like to start my talk really by introducing what I mean by simulation-driven design optimization. And so the idea is that we have
Quick second. Sorry. This is making your face look really weird. Okay, go ahead.
So the idea is that we have some experiments, and we have developed some numerical models that we have validated against experiments. And basically, what we want from the simulations is we want simulations that have two things. So we want simulations that are tractable, but we also want simulations that are predictive as well, right? So what I mean by predictive is that oftentimes we want to capture efficiency or performance. We want to predict points of failure, or sometimes we want to predict when you're going to have catastrophic rate events. So for instance, I do a lot of work on CFD for energy applications like gas turbines, IC engines. In those kinds of systems, we're interested in thermoacoustic instabilities, lean blowout, flashback, things like knock, and stuff like that. So we want simulations that can capture all of these phenomena here. And the idea is that once we get simulations that are accurate and tractable, we can actually couple the simulation with a design optimizer. And what's going to happen is that the design optimizer is going to run simulations at specific conditions, and it's going to progressively try to guide us to designs that are promising. And once we have that, we can go ahead and do some validation by building physical prototypes. So why do we want simulations? Well, the first reason is because we can easily test our design in regions that is hard to do. So if, for instance, you have thermoacoustic instabilities, you might damage your engine. But if it's a simulation, it's possible to do that. And also, the other reason, which is huge, is that we can adjust parameters that are hard to vary in experiments. For instance, if you wanted to change geometry, you'd have to go build a new device. But with experiments, you can change the geometry and do that easily. At the top here, I have a simulation of sort of like a heavy-duty diesel engine, and you can see the piston and how it goes up. And the red spot that shows now is basically when you inject the fuel into the engine. So these are the kind of applications that I'm interested in. Basically, simulation-driven design optimization, and specifically for combustious or open energy devices where you burn a fuel to generate some energy. So first, I also wanted to talk a bit about that process of design optimization like I had in the previous slide. So the idea is that you have a simulation, and you can run simulations at different conditions, and when you get the results, you pass it down to an optimizer. And then the optimizer, in return, gives you a new set of points to run. And so you basically run a new set of points at those conditions, and then you get the results, and you continue the cycle on and on like that. The goal of the optimizer is to lead you to the lowest or highest point based on your design objective. So your design objective might be to increase the thrust of a jet engine. It might be to minimize fuel consumption. But the idea is that the optimizer is going to take steps and guide you in the right direction to take. So in terms of simulations, most of the types of simulations that I run is called computational fluid dynamics, or CFD. The basic idea is that we're using numerical methods to solve the PDEs that govern flow of a fluid. So what are some of the challenges that we face? The first one is that CFD simulations take a very long time to complete, even when we're using several processors in parallel. Running CFD simulations, if you wanted to use a full resolve all the scales, is going to take several months, or even in some cases several years. So it's just impossible to run. What that means is that usually the cost of CFD simulations is a huge bottleneck whenever you're trying to do simulation-driven design optimization. And so what we have to do really is we have to use simplified models. So we make assumptions, we simplify the models so that it can run fast enough. So that's basically what we do. And so what are some of the goals of my research group? We do research in sort of these two areas. The first one is to improve the accuracy of these reduced simulations or the simplified models. Or you can sort of think about it as trying to make high fidelity simulations more practical. And so sort of we can think of that as trying to work on the left side of that cycle. But we'll also do some work on the side of optimization, which is how do we create design optimizers that are efficient with the way they use simulations. So what do I mean by that? You might have an optimizer that needs to run 100 simulations to get you a good design. But you could design an optimizer that's more efficient, that only requires 50 instead of 100 to get you a good design. And so you can make progress on both sides of the cycle to reduce the overall time for that design cycle. So that's the idea. All right, a bit about the kinds of simulations that I run and why it's so challenging. This is what I like to call multi-physics, multi-scale, multi-species. And so first, the multi-physics. What does that mean? Well, it means that we have to capture multiple physical phenomena, right? So for instance, you have a gas turbine in your engine, or even your IC engine, you have a spray. You have a fuel that comes in as a liquid spray jet, and you can sort of see that it comes in as a blob, and it breaks up, and then atomizes and evaporates. You have your turbulent flow field itself that you have to capture. We have chemical reactions if you have combustion taking place, right? We have acoustics, which is basically pressure waves in your domain. And then we also have heat transfer as well. You have to have a simulation that captures all of these effects. The problem isn't capturing these effects as much as it's the interactions between them, right? So you can have your spray that comes in and that can generate turbulence. Or you can have your heat transfer kind of affect the chemical reactions. Or you can have the interactions between chemistry and turbulence, which is a big deal, and it's really tough to capture. So that's the multi-physics part. It's multi-scale because the range of time scales range from about a nanosecond to the order of seconds. You have to capture what's going on across those scales. You have a large range of scales in space as well. And then the last one is if you have chemical reactions, oftentimes you have several species you have to capture. So if you have hydrogen and oxygen, right, we know that that should give us water. But you don't just get water from hydrogen and oxygen. You have several steps and minor species that get formed in the process, and you have to capture what's going on with all of them. So these are the equations that we typically solve. You have to solve an equation at the top called the continuity equation. You can get the density from there. We have a linear momentum equation. We have three equations, I equals 1, 2, and 3. From that, we can solve and get the velocity in the x, y, and z direction. And then, if you have significant changes in temperature, you have to solve an equation for energy as well. And that's what I have there. The problem, though, is this equation that we have for the chemical species. So this is not just one equation. You see I have yk, which is the mass fraction of the species, and k goes from 1 to n. So if you have 500 species, you're solving 505 equations at each time step, at each cell. So the takeaway is that if n is large, we need to solve several PDEs because we need to keep track of a large number of chemical species. And that makes it very expensive. All right, so I'll go a bit into, I guess, the two sides of that coin that I mentioned. But before I do that, I just wanted to just bring us back here and sort of put things in context. The first part of the talk is going to focus on the left-hand side, and then the second part is going to focus on what I have on the right, which is on optimizers. And so I'm going to talk about some of the work that we're doing in my group on trying to make these two sides more efficient. So the first part, I'm going to talk about specialized neural networks for reduced order modeling of turbulent combustion. And I'd like to acknowledge my collaborators. So this work was done while I was at A&L as a postdoc before I joined LSU. And so I'd like to acknowledge Pinaki Pal, who is the research scientist, Cody Nuno, who has now left Oregon, and Preeti Shkundu as well, who worked with me on this project. So the basic idea of a neural network is I have an input, which I'm calling x here. It's an input vector. I'm trying to make a prediction for an output vector y. This is a supervised learning process. I have some hidden layers. I have weights w and the bias vector, set of biases, that's b. And the idea is that for each layer, I apply a linear transformation and I apply a nonlinear activation function. And I do that from the input layer all the way to the output layer. I have a loss function that measures sort of like the distance from my predicted value to my actual value that I'm trying to find. And I can use some sort of gradient descent algorithm to sort of update the weights so that the predicted and the actual values match. So that's sort of like the basic idea. It's a supervised learning process. I gave my network examples. It learns from that, and then in future I try to use those, what it's learned to make future predictions. What I'm going to present here is slightly different. The idea is that instead of making one network make a prediction, why don't we employ multiple neural networks to make the same prediction? The idea behind this is to achieve better performance by creating networks that are specialized. So for instance, I'm in the mechanical engineering department at LSU. We have different specializations. I have some of my colleagues work in energy, some work in biotechnology, some in materials. And everyone has his own expertise. The reason for that is because we can better collaborate and make and be able to be more efficient by having an area where you're specialized in. It's sort of the same idea here. The idea is that I'm going to train all these models, and each of them is going to have a specific region where it's an expert. And model 1 has its own regions, model 2 has its own regions, model N has its own regions. So the idea is that I bring in an input signal X, and all of these neural networks are going to compete for that signal. So they're going to compete. The network, the guessing network at the top is sort of like monitors the process. And anytime a neural network performs well for a signal, in the future it's going to reward that network with a better signal. So if you do well, you're going to get better in future, and if you don't do well, you're going to get worse in future. And the result of that is that your input space gets partitioned. It gets broken up into smaller bits, and in each of the regions, a given neural network is an expert in making predictions there. What's the intuition for doing this? Think about trying to make a prediction for the data points we have there. So we're trying to find a function of, we're trying to find y as a function of x. You can sort of think about trying to get a single function that fits everything. But maybe a smarter way to do that is to break down that x interval into 3 bits, where from x equals -1 to 0, I have one model, and from x equals 0 to 3, I have another one, and then I have a third one in that region. The idea is that by doing that, I can use a simple linear relationship to make my predictions as opposed to something that's nonlinear. So that's the idea, is to have simpler models, multiple simple models instead of one complex model. That's the idea. And this approach is what we refer to as a mixture of deep experts. I'm going to call it modes moving forward. So the loss function that we have is shown there, and basically this is a loss function for a given expert k within a system of n experts. E sub k is the error, so it's the predicted minus the actual value you're trying to predict for that expert. Pk is the prior probability that an expert is the best, and that's the probability that the gate network gives to us. Beta is a parameter that tries to make the experts separated even as the errors go down. And the motivation behind that loss function is that if we differentiate that loss function, what happens is that the way the learning rate for updating the weights gets scaled by alpha sub k. If you think of what alpha sub k is, if e sub k is small relative to the rest of the experts, then alpha sub k is going to be large, which means that that expert is going to learn faster. The reverse is true. If e sub k is large, then this alpha sub k is going to be small, and that means that we're going to slow down learning for that expert. So that's how they train. In terms of the loss that we use for the gated network itself, it's just the standard cross-entropy loss of classifiers. So now comes the application. So that's the idea behind modes itself. And in terms of the application, what we've chosen here is something called the Flaminant model. It's widely used in combustion modeling, turbulent combustion modeling. And the idea is that even though I mentioned that we have this large number of chemical species in a flow field, in some cases, we can actually simplify the problem and create what is called a set of control variables. And the idea is that if the chemical reactions are very, very fast, we can use some scaling laws to say that, well, even though it's very fast, all of my mass fractions are just a function of z, where z is the mixture fraction. If we have fast chemistry, but we have non-equilibrium and steady effects, then z is a function of chi and c, where c is some progress of the reaction. And under some cases, if it's not isobaric, we have to add z, chi, c, and p in order to predict the mass fraction. All right. The big picture to take from here is just that the more complex the problem is, the more variables we need to add to that model. So the way this is solved is that you run a very simple case, and then you take the result and you store it in a table. So it's a tabulated model, and then what we do is we try to take the table and store it in memory so that when we run the CFD, we don't have to solve the chemical species in real time. All we have to do is look up the table and interpolate and pick out the result. That saves a lot of time. The problem is that storing a table is intractable if this vector is high dimensional. So if you have one or two variables, it's fine to make a table, but as you increase the number of variables, control variables or dimensions, it becomes intractable, and that's because of the memory demands, right? So you go from 1, 2, 3, 4, 5, 6 dimensions, and the size of your table basically increases exponentially. So the idea is that to apply modes here, and instead of taking the table and storing it in memory to predict the mass fractions, instead we're going to learn that table using a neural network, using a mixture of deep experts, so that we can make predictions in CFD as opposed to relying on the tabulation approach. So that's the application here. The good thing is that for the neural network, we only need to store the model parameters. We don't have to store anything else. So these are some of the results that we get. On the bottom, I have a solid line, which is the ground truth. So that's the actual solution we're trying to target. The modes is a mixture of deep experts, and SA and AND stands for using a single model. So trying to fit all the data points using a single neural network, and to sort of see how that works. This is showing the mass fraction of hydroxyl radical as a function of the mixture fraction for different levels of the progress variable. And what we see here is that the mixture of deep experts, where we have neural networks that are specialized, that fits the data points very well. So you can see that it matches well with the ground truth. But trying to use one neural network that just doesn't work well. You can see significant errors there. This is also showing another result for CH2O or formaldehyde. And you see the same thing, that the dotted line, which represents a single neural network, doesn't do well. So basically, you see significant errors because it's too complex. But when we split the problem into different bits, it's able to learn a lot better. This result is showing the mean squared error that we get. So you can use, on the left extreme, you can use one expert, which means you use a single neural network to fit everything. Or on the right extreme, you can use 8 experts to fit the data. So you split the problem into 8, and you have different experts learn how to make predictions there. And what we see is that if we use a 4x4 network, so 4 neurons, 4 layers, versus 12 by 4, 12 neurons, 4 layers, you can see that the errors go down as we increase the size of the network. So go from the gold to green to blue. But another trend occurs when we increase the number of experts, even if the size is the same, right? And then this is the mean square error for CO2. We have OH, we have CH2 and CO, and the trends remain the same. In general, we see that the errors go down based on the specialization that we've done. So basically, they work better due to the specialization that occurs. We also did something else, which is the last result I showed was for a 4D table. So we had 4 variables. And so in this case, we tried to extend it where we had 5 control variables. In this case, the size of the table had 50 million entries, or 29 gigabytes, which might begin to introduce storage issues in CFD. But in contrast, the neural network was about 1 megabyte. And again, we see the results that using the specialized neural networks works a lot better than trying to fit everything with one. All right, so we did an actual 3D CFD simulation. These are the details of the setup. So this is called a spray A simulation. It's relevant to diesel engine conditions. You have a spray that comes in through a nozzle. You have spray breakup. The fuel atomizes and evaporates. You have mixing between the fuel droplets and the air. And then ultimately you have a flame that develops due to that. These are the details of the cell counts, 21 million at 1 millisecond. We use the RANS model. We also did some LES as well, which is what I'm going to be showing. The temperature of the gas around was about 900 Kelvin. Okay? And the simulation took about 4 days using 72 processors. So this result here, you cannot see it right now, but there's a blue line that's forming there due to this spray. And you can sort of see the temperature on the right and OH on the left. OH really comes up when the temperature goes high because it's related to high temperature chemistry. But let's see if I can make that run again. So you can see this mixing is occurring, and then at some point you begin to see that the temperature begins to rise. And in this case, the temperature and the OH radicals and everything is predicted by the neural networks. We also have some results here for ignition delay. So ignition delay is basically the time that elapses between when you inject the fuel and when the spray develops. And you can see that for experiment, the modes approach really is close to experiments. There's a slight error, but it's not that high. And then I also have a plot of the maximum temperature as well, and we can see that it predicts it well. And at the bottom, I have the rate of heat release as well, and that's also well predicted. All right, the last thing I wanted to talk about here is mention that the approach does partition your input space. It turns out that the partitions that it gets is actually physically intuitive, right? So we decided to run a test where I have some data points. On the y-axis, I have the progress variable, and on the x-axis, I have something called statistical anticipation rate, okay? And just based on these two quantities that I have, I can kind of tell as someone who works in the field that what I have at the bottom here should be my pre-ignition zones. So you have a reaction fluid, but the reaction hasn't occurred yet. And then what you'd have here is what occurs when it's actually ignited, in the process of igniting. And then at the top is what happens when ignition has already occurred, so your combustion product. So we decided to run this problem and see what kind of partition we're going to get. And if the way the space is being divided is actually intuitive physically. And this is what we get. And so we see that the model is actually dividing the space in a way that makes sense from a physical perspective. The pre-ignition zones are assigned to expert 3, ignition zones are assigned to expert 2, and the post-ignition zones are assigned to expert 1. And so this was interesting to see that it's not random, but it actually makes sense from a physical perspective. And if I did not know anything about this problem, this would have been a way to actually understand better what's going on in this problem. All right, so to summarize the first part of my talk, I presented a mixture of experts approach for developing specialized neural networks. I would say that even though this was applied to turbulent combustion problems, this is something that can be applied to a range of problems, as long as the function you're trying to approximate is complex enough. We show that it led to better representations and accuracy compared to using a single neural network. And we also show that the global characteristics, like the ignition delay, was well predicted. And then in the last slide, I show that the partitions that we get are actually physically intuitive. And right now, we're trying to extend this to scrambled engines to see how this performs for those kind of applications. Lastly, I want to acknowledge the resources that we use and funding from DOE's office when I was in Oregon. We used clusters called Blues and Bebop at Oregon National Lab. All right, so that's the first part of the talk. The second part, I'd like to talk about the second side. So we want to get simulations that are practical and fast, but we also need to get optimizers that are more efficient in finding out the best design that can take those simulations and use them to figure out the best design that we can get. So for this work, I would like to acknowledge my student, my PhD student, who is right here, who has done a lot of good work and worked hard on this project. And a lot of what I'm going to be showing today is really his work and what he's done. And so I'd like to acknowledge him for that. So I'd like to first start by talking about the idea of swarm intelligence, because it really fits into what we're trying to do here. So the idea behind swarm intelligence is that it occurs when you have an individual agent that's simple all by itself, but it can work with other agents to cause global effects to emerge. Okay? The idea is that it interacts with its environment and with other agents to accomplish tasks that by itself is impossible to accomplish. So think about a single insect, for instance, like an ant, right? It can't really do much, right? It can maybe lift a few things, but what happens is that when they work together, they're able to accomplish complex tasks. And that's the big picture of swarm intelligence. So, well, we can sort of think about other examples. So first, I mentioned ants, right? So we know that ants usually, when they're trying to forage and look for food, they'll actually work together and collectively choose the shortest path together. We have wasps and termites that build nests in mounds. So this is an example of a mound. And they can get pretty tall, several feet tall actually. It's impossible for one of them to do this by itself, but they can work together and do this collectively. We have flocking in birds and fish, and also bees as well. When they're looking for a new home, they would often scout and look around and try and select the best location that they can find. So what does all of this have to do with what we're talking about, optimization? The idea is that we can do something similar. We can have this form of agents that cooperatively work together and try to find the maximum point or the minimum point on a surface, right? So in this case, I have a function. You can sort of think of this function as having I have a variable x and y, or x1 and x2, and the height is the objective we're trying to achieve. So we're trying to maximize the height on that, right? And so the question is, how can we put a swarm or some agents on that surface and work together to find the maximum point? So in line with that, I would like to introduce what we call deep Hive. And it's an approach that we've developed in my research group. And the goal of deep Hive really is to develop optimization policies using reinforcement learning. The idea behind reinforcement learning is that you have an agent that's within an environment. The agent can take actions within that environment, and whenever it takes an action, two things happen. First is it gets an updated state. So the initial state was state s sub t at time t, but now the new state is s sub t plus 1. So it gets an updated state, but it also gets a reward for the quality of the action that it took. So the idea is that if it takes an action that's good, then it's going to get a good reward. But if it takes an action that's not good, we're going to punish it. And so you can sort of think of the first part of my talk as focusing on learning by examples. In reinforcement learning, we try to learn from experience. If you think about it, that's how we learn, right? The first time you taste a candy as a kid, it tastes sweet, and so you want to try it again because you get a positive reward. If you touch a live wire, you're going to get electrocuted, and you'll know not to do that again. So that's sort of the idea. So the idea is, in summary, you try to learn to perform the best actions within an environment by trying to maximize reward. So that's what we're trying to do here. The goal of Deep Hive, like I said, we're trying to discover optimization policies. The kind of applications that we're interested in really is the applications where the function evaluation is expensive. What do I mean by that? So think of trying to optimize combustion process to reduce emissions, or trying to discover new materials, or trying to design a battery power pack to optimize cooling. In all of these cases, anytime you have to go and take a step and do an experiment or run a simulation, it takes a long time. So that's what I mean by it's expensive. Expensive might mean that it takes a while to do it. It might mean that the simulation takes a long time. It might mean that it costs a lot of money. The idea is that we don't want to run a lot of these simulations. We don't want to have to evaluate the model a lot of times. That's the idea. So on this slide, I'll talk a bit about the connection between elements of reinforcement learning and Deep Hive. So at the top, I'm going to have key elements of reinforcement learning. And then at the bottom, I'll have how those relates to what Deep Hive is trying to do. So first, in reinforcement learning, a key element is the environment. And in this case, the environment is simply the function that we have that we're trying to optimize. That's the environment. That is where the agent lives and where it can take actions. The state is simply the position and past objective values of all of these agents, right? So I have the agents sort of in the white circles, and that's the current state of the system. I can take actions within that environment, and to take an action simply means that you can sort of see the red arrows there. It means that I can update the position or location of these agents, right? So I've taken an action, and whenever I take an action, I'll see how good it is, right? Did I get a better objective, or did I get a worse objective, right? And so we are going to reward these agents, and that's based on the quality of the design that it finds. Okay, so a policy that doesn't find a good location is going to be penalized, and an objective that finds a good location is going to be encouraged in the future. So that's the idea. Encourage good actions, discourage bad actions. We want to decrease the probability of taking bad actions. So we have two stages here. The first one is we're going to take a bunch of agents that know nothing, and we're going to try and train them to learn how to optimize. And that is called the policy generation phase. And so what we're going to do first is you select an optimization problem, some sort of function, and we're going to set up the reinforcement learning environments, set up the state, actions, words, all that stuff. And then we train the agents using something called a PPO algorithm, which I'm going to talk about in a bit. And once we're done training, we're going to get something called a policy. It's a strategy for updating the location of the agents. And what we want to do is save the best policy that we can find. Okay. So the PPO algorithm was developed in 2017. And the idea is that if we want a policy that's good, we can decide to maximize this loss function that I have here. So pi theta is the current policy, and pi theta old is an old policy or some baseline policy that serves as a reference state. And E there is the expected value, okay? A is the advantage. So the advantage is simply a measure of how good a given action is. If it's a good action, it has a good advantage. If it's a bad action, it has a bad advantage. So you can sort of think about trying to maximize this function, right? If A sub t is negative, then that means that that action is going to be discouraged in the future. If it's positive, it's going to be encouraged. The probability ratio sometimes, which is the pi theta over pi theta old, can be a problem because sometimes you have a policy that looks good locally, but if you take a large step, you might fall off a cliff, so to speak, and get a really bad policy, you cannot recover from that. So what we do to prevent that process is to clip the step. So you can see a clip function here. where we limit the change in RT to be between 1 minus epsilon and 1 plus epsilon. So finally, we come up with the final loss function that we actually use. So we maximize this function here. I have the L clip, which is from above. I also have a term that we use to update something called the value function, which I can talk about later. And then we have another term here that's an entropy term. When you maximize it, you tend to increase your exploration because you don't want to stick with a policy without exploring if there are other policies out there. That's good. All right, so the left part I've spoken about, we do the policy generation. And then once we're done with that, it's time to deploy the policy and actually test it, right? So we have a policy, pi theta, which is actually just a neural network. The neural network takes in the states, and it gives you an action that you should take in that space. So that's what we do. We initialize the agents. We generate actions from the policy, the best policy that we saved. And then we update the agents within that surface and have them talk to one another and move around. And then we repeat that process until it converges. All right. So in terms of the function that we're using here, it's a benchmark function that's really common. It's called the Cosignature Function. The equation is described here. I have two variables, x1 and x2. The goal is to find the value of x1 and x2 that maximizes f of x. Okay. Now this function looks simple, right? I can just go and pick the peak there. The thing is, in practice, you don't know what the function looks like. So you're really searching in the dark. And the goal is to use the policy to guide us to the top surface, even when we don't know the function. In this case, we do know the value that f max is actually at 0.1 times d, where d is the number of dimensions that we have. So in this case, d is equal to 2. So the maximum point is at 0.2. What I have at the bottom is the same thing, but it's sort of like a control plot looking at it from the top, which I'm going to use more often moving forward. All right, so we compared what we got from Deep Hive with some few other optimizers out there. So we have particle swarm optimization, which is PSO. It's also a swarm intelligence-based optimizer, but it's something that's manually designed, right? It's not learned automatically like we're doing here. We also have one called Gnode and DE as well. These two are genetic type algorithms. The neural network that we used to predict the policy is 2 hidden layers with 32 nodes in each. The input layer had the input was about 4 neurons. And training took about 2 hours on a workstation, so it doesn't take that long. And so on the next slide, I'll show what we get. So remember that we're trying to find, we're having agents and we're trying to get them to find that location there, right? So in this case, the maximum point is right at the middle, where we have that white star there. So this is what we get. I'm going to pause, well, I'm going to leave that to run. On the left, I have the initial policy, so it's a random policy for training. And we have the agents in the red dots, and they sort of move around, and they're trying to find the maximum location. And they don't really succeed, they kind of bounce around and get caught up in that corner over there. But after training, you can see that very quickly they're able to all converge to the center, which is where the best location is, right? I'm going to let that play just one more time. And you can see that it's random, and then they all move and update their positions. So the change in position at every time step is predicted by the policy that we learned, right? So they learned how to optimize, but that was all due to that learning from experience that we just showed. All right, this slide is showing the results, the actual results. So on the y-axis, I have the maximum objective that you find, so higher is better, right? You wanted to find the maximum location. On the x-axis, we have the number of functional evaluations, so it's how many times do they have to call that function. Keep in mind that we want to keep that number as small as possible because this is a, sort of like a toy function. But in practice, every time you have to call that function to evaluate it, you're waiting for hours or even days, right? So what we see is, well, the other thing to keep in mind is that this is on a log scale, so the separations are a lot higher than it looks. And then whatever you see here is averaged over 25 different trials. So we just repeat the process, and then we average the value of the function. Because if you do it just once, you might get lucky and get a good result. So what we see here is that in general, the deep Hive is able to get a higher objective than the rest. Finally, the G-node catches up, but PSO and DE, they sort of converge prematurely to about 0.176 or 0.18. And so on average, deep Hive takes about 130 functional evaluations to reach 0.19. The other two, DE and G-node and PSO don't get there. G-node gets there, but it takes 350 functional evaluations, so it's a lot slower in getting there. We try to look at the effect of basically varying the number of agents we use. So we trained using 7 agents, and the question is, well, what if we wanted to use 5? What if we couldn't use 7? What if we wanted to use 10? The good news is that it scales well. So as expected, 5 doesn't perform very well, but it still finds the optimum point at 0.2. 7 performs better, and 10 even performs better than that. So you can train with 5 and use 10 when you're deploying it, and it works just fine. All right, this is another animation showing the difference between 7 and 10 agents. You can see that with 10, it gets there very quickly. With 7, it does explore a bit more, and so it takes a little bit longer. What happens if we try to increase the number of dimensions? So remember that the Cosignature function, it has a parameter called d. So if you increase the value of d, you can actually have a 1-dimensional version or a 3D version of the function I just showed you. The only problem is that as you do that, the number of local maximum increases. So think of the local maximum points as potential traps where your optimizer can get stuck in, right? So if you have a 1D case, you only have 5 peaks. If you have a 2D case, it's 25. For 3D, it's 125. For 4D, it's 625. So it gets a lot more complicated. But even though we trained it on a 2D function, it's able to work well for 3D and for 4D. It takes a bit longer to get there, but it's still able to work for even higher dimensions. So we were wondering, well, it's working well, but everything I've showed so far is we trained it on the Cosignature function, and we're testing it on the Cosignature function as well, right? So even though we varied the number of dimensions, we varied the number of agents, it's still the same function. So we're sort of curious to see what's going to happen if we give it a totally different function. The reason for that is because there's a risk that the agents are memorizing the location of the global optimum, and they just always go to the middle, regardless of what happens. So these are some of the results we get from there. The one on the top left is called the Martinez function. And you can sort of see that it's not a lot better, but it's somewhat comparable to the rest of the optimizers. So it's definitely learning a policy for optimization. And we also compare it to what's called a 6-on-camel function. In this case, it actually has to separate global optimum points, which are not in the middle. And it's still able to perform reasonably well. You can see the red dotted line there for deep Hive. This is another one that we tested it with. It sort of performs better than both DE and PSO, but it's kind of similar to the way the G-node performs. And then finally, we have a last function, which we couldn't find a name, so we called it function 2. The top one is function 1. We kind of made up these functions just to test it. And you see the same trend as well. It actually doesn't do that badly, even though it never seen this function before, right? So we generated a policy based on Cosignature function, and then even with unseen functions, it still performs decently well. These are some animations of how it finds the optimum for this function. You can sort of see that on the left, the location of the optimum is sort of in the top right corner. It's able to find it. And on the one on the right, for function 2, it's able to also find it there in the middle. So in summary, I've presented a reinforcement learning-based approach for generating optimization policies. We compared the results we got with PSO, DE, G-node, other optimizers. We looked at the effect of changing the number of agents and the number of dimensions, as well as the potential for generalization to other functions. And what we saw was that we got good scaling performance when we changed the number of agents. And even when we used higher dimensions, it was able to find the global optimum. And what we did was that we took the policy we generated using Cosignature Function, extended it, and it worked decently well for even functions that it had not seen before. And sort of what we're working on right now is we've done these two stages here, which is to test it on like a 1D function. We've extended it to like a 2D type surfaces. And what we're working on now is to try and extend this to actual CFD optimization studies to see how that performs. We're also thinking of introducing things like a local search component to make it a lot more efficient. All right, that's the end of my talk. Thank you for listening. I'll be happy to take any questions.
Let us thank the speaker again for his interesting talk. And we have time for questions, so people here just ask questions, and in Zoom you can use the raise your hand feature, and then our admin can unmute you and you can ask your question. So who wants to start? Yes, please.
What is an agent if you have x1 and x2 two-dimensional problem? What is the meaning of each agent? You know, is that something, one agent is trying to just move towards x1 direction and another towards x2 direction, or no? There are some sort of artificial just meaning. I'm using them, some, like you can say just CPU, right? To process that, information. That's my question.
So think of an agent as an artificial version of what I showed, like you have like a biological organism, like an ant or something like that. An agent is sort of like an artificial version that can take an action on a design surface. The action is to update its position. What we do is the position is updated independently. So if you have x1 and x2, you can take a step in x1 and x2 independently, right? And then your distance would be the Euclidean, distance based on that. Yeah, exactly. So you update the positions separately, independently. That's why it works for multiple dimensions, because each dimension is sort of independent in the way it's updated. So that's like the basic idea. An agent is something that can take an action within an environment.
Some sort of sensitivity analysis, right? It doesn't mean if you have 10,000 variables, you can have 3 agents. Each agent randomly change variables to see what would happen. Then they cooperate to find the best.
So the thing is, each agent doesn't just know about it. The reason it works better is because an agent has its own current state, but it also gets information from the other agents. So there's a lot of sharing that's going on. Which is why if you have 3 agents, it might not work very well because you don't have enough information from all of them. The more agents you have, the better, but each agent is updated not just based on itself, but based on what others can see at a given point in time. So that's the basic idea.
Just following up on the comment, how is it affected by the architecture of the parallelism?
So the thing is, all of the agents, so are you talking about the neural network itself or the way that they are arranged?
Because they are sharing the information.
Yeah.
So that's why, if they are sharing the information, are you using some sort of shared memory architecture?
I see.
So that's what I'm trying to get at.
Yeah, so all of them right now, they all have the same memory. So we're not doing any communication between them. Because, the thing is, even the neural network is shared among them. The only thing that's different between them is the state. So they all are in different states, but the policy network that's used to determine what actions to take is the same, the weights are the same, right? So because of that, they all are on the same node, and so they all see the same memory. So there's no, at some point we might have to do what you're talking about, but right now it's just all on the same one.
Do we have more questions? I have one. I think in the one image for your function you had 2 maxima shown. So what does happen? Is always one found, or is it 2 of them?
You mean this one?
I think
The
this
one
one. Yeah.
So the thing is, for the 6-sum common function, you can, anyone you find is valid.
Yeah, but what does your agents do? Do they find this one? Do they find that one? Or do they switch between them if you run it 10 times?
So the thing is, usually they just randomly converge to one because they're not memorizing the surface, right? So
yeah.
It's not like they know that, oh, there's an optimum at the upper one and they always go there. It's not the surface, it's the policy that they use to update, and it seems to work across different types of problems. So
is it 50-50, or is there some preference for one or something?
I'll ask my student there who worked on it. Did you see like any differences in the?
No, they just find one, right? And then all of that agents try to meet that one.
Okay.
Yeah.
Interesting.
Yeah, so what happens is, if you look at the image that I shared, the best agent is frozen at a given point in time. So once one gets there, the rest of them try to converge towards where it is.
Okay.
They have knowledge of where the best one is, and they try to go towards that while still moving randomly, so to speak. So
I have one last question. So in this picture you showed, the maxima were quite a distance. What happens if you do them close together? Can they still find it?
can you? Oh, you mean like when like you initialize them, like the?
No. Can you go back to the image? So I think here the distance is quite large. But what happens if we move this that they are really close?
Oh, I see.
Because this makes a challenge if they are really close, because then you can hop between them probably.
I don't see why it wouldn't do that. I think it should be fine, just based on the way it works. The reason for that is because I think it's probably even easier to find when they're close together. Because again, it doesn't know that there's a different one somewhere else. It's just a local function.
Just was curious what happens if they are close together. So,
yeah, we haven't tried it. We haven't had a function like that, but I assume it should still work well.
Yeah.
Yeah.
That would be interesting, just.
Yeah.
Okay. Do we have any questions in Zoom?
I see something on the chat. Okay, it's just from Christopher.
No, things looks good. Okay, so if you don't have any questions, let us thank the speaker again for his interesting.
I think he has a question.
You have one?
Okay. The whole process, is that possible to model everything with one learner? Just machine learning, because you have learner for simulation and learner for optimization, right? Why not combining all of them with just the whole process in one learner?
Are you talking about the first part of the talk or the second?
Yeah, the first part of the talk, because the whole part was we have simulation, then we have optimizer, they iteratively talk. So if I understood that correctly, you have a learner for simulation, you have another learner for actual optimization. Why not combining them into one learner?
So the idea behind the cycle that I showed is that you have a simulation that's running, and then on the other side of the simulation, you have an optimizer that tells you what types of simulations to run. So the neural networks have like separate tasks. One is telling you, well, run a simulation using the velocity of XYZ, using this shape parameter. And then the second one is you have a series solver, and the neural network enhances that solver. If you had like a purely surrogate-based approach, then yeah, maybe you could do that. But in general, the tasks are separate, so I'd expect this to be different.
Thanks.
Okay. More questions? Okay, so let us thank the speaker again.
Stop the recording.
No, he's stopping recording, so he's good. Yeah. Okay, thank you again for the talk. It was quite interesting.
Thanks for inviting me.
So when we record it, we upload it. So.
And then
Recording stopped.
it's going to be on YouTube,